So welcome to the very last section that we're going to be studying before we take our test next week, Tuesday. We're going to be solving logarithmic and exponential equations today. So exciting to finally see what all this stuff that we've been learning comes together so that we can finally solve some equations. Our homework is on page 596 to 600. It will be on the slide at the end of this presentation. You'll do numbers 1 through 4 all, 9 through 14 all. But then you'll do multiples of 3 on 15 through 24 and 39 through 51. All right, so let's go ahead and get started. So we're going to use one-to-one properties to solve our exponential and logarithmic equations. And so we've got our one-to-one properties written right here. So we want to take a look at these. The first one is, I'm going to put my glasses on, a to the x is equal to a to the y. Now notice that a and a have the same base. So this only can occur if the exponents x and y are equal to each other as well. So x has to equal y. The same thing when I have a log with a base of a of x and it's equal to log base of a of y. Notice that the log terms both have the same base. Therefore, the arguments of x and y have to be equal to each other. We're going to use that information in order to solve equations here. So let's take a look at our first example. First one is 5 raised to the 2x plus 6 is equal to 5 cubed. So the base is 5, meaning that our exponents are going to be equal to each other. So we can set the exponents equal to each other. 2x plus 6 equals 3. And then we're going to solve from that. We're going to subtract 6 from each side, and we're going to get 2x equals negative 3. And then we're going to divide by 2 to get our final solution. X will all be by itself, and x is equal to negative 3/2. So once we get to an x equals something, we have reached our solution. In this next one that we're looking at, right here, it's now a log term is equal to another log term. The base of it, this log and this log, have a base of 10. Base 10 for each of them. 10. So I can say that the argument 7x plus 1 is equal to the argument of the other log term 15. So I'm going to set that equation up. 7x plus 1 equals 15. Then we're going to go ahead and solve for that. So we subtract 1 from each side and we get 7x equals 14. Then we're going to get x all by itself, we're going to divide by 7 and we get x equals 2. Another way that we can approach exponential functions is to rewrite them as a logarithmic term or a logarithmic expression. So let's remind ourselves how we can take those equations and go back and forth. Remember, Miss Lenhoff had that cute little story. Ben went out for a walk, fell over a log and broke his knee. Benny. But just to remember the placement when you go from exponential equations to logarithmic equations. So we're going to go to this first equation. 3 raised to the x is equal to 12. Well, x is in the exponent. It's really hard to find, and 12 is not something that cannot be rewritten with a base of 3. So I'm going to rewrite it as a log expression or equation. So I have log base 3 of 12 is equal to x. Now x is all by itself already, so I can grab my calculators and type this in, except for one little thing. I don't have log base 3 on my calculator, so I am going to use change of base. So base 3 of 12 becomes log 12 divided by log 3. Now I can grab my calculator and put in log 12. Don't forget to close your parentheses and divide by log 3. Once again, close your parentheses, and then you're going to round to the nearest 3 decimals as given in the directions. So x is equal to 2.262. Let's try the next one. The x in the exponent is not by itself, so we have an additional step here. So I am still going to write this as a logarithmic equation. So I have log base 5 of 45 is equal to x plus 2. Now x is not by itself, so we want to subtract 2 from each side. So we'll have log base 5 of 45 minus 2 is equal to x. Now x is all by itself. We're ready to do some calculations, except that we don't have a log base 5 on our calculator. Once again, we're going to do a change of base, but the change of base only applies to this part. It does not include the negative 2. So it's going to be log 45 divided by log 5. So we're going to grab our calculators and do log 45 and your parentheses, divide log 5, close those parentheses again, and then subtract 2. And when you hit enter, you get x is equal to 0.365 when rounded to the nearest 3 decimals. Okay, these ones are going to be done very similarly. We're going to do this one first. So we have 5 times e raised to the 2x equals 15. But before we write it as a log equation, we're going to divide by 5 so that we have our exponential expression all by itself. So when I divide each side by 5, I get e raised to the 2x is equal to, and 15 divided by 5 is 3. Now I can rewrite this as a logarithmic equation. So I'm going to have log base e, but remember log base e is the same thing as the natural log. So the natural log of 3 is equal to 2x. X is still not by itself, so one last thing I need to do is to divide each side of the equation by 2. So I divide each side of the equation and I get x is equal to the natural log of 3 divided by 2. Grab your calculators. This is where we can do this. We're going to type in natural log of 3, close your parentheses, and divide by 2, and set it equal. And to 3 decimal places, you're going to get x is equal to 0.549. On this next one, we have even more things to do before we can write that logarithmic equation. So the first thing we're going to do is add 5. We want to get this non-exponential expression onto the other side. So we're going to add 5 to each side. That leaves that 3 times e to the x plus 1 equaling to 7 plus 5, which is 12. That exponential expression is still not all by itself. It's being multiplied by 3. So we will divide each side by 3, and we get e raised to the x plus 1 is equal to 4. Now we're ready to write it as a logarithmic equation. So it'll be log base e of 4, or remember log base e is the natural log. So we'll have the natural log of 4 is equal to x plus 1. One last thing to get x all by itself is we're going to subtract 1 from each side of the equation. So subtract 1 and we get natural log of 4 minus 1 equals x. So we're going to once again grab our calculators and we do natural log of 4, close the parentheses, and then subtract 1. And we're going to get x is equal to 0.386. Excellent. So just as we were taking exponential equations and rewriting them as logarithms, we're going to do the other way around too. If I'm given a logarithm and the argument happens to have the variable, I can rewrite this as a exponential equation, and then I can solve for x a little bit more easily. So on this one, I've got a 3 times log base 2 of x is equal to 12. Well, I want to isolate the log part of the term, so I'm going to divide each side by 3. And I get log base 2 of x is equal to 4. I can rewrite this as an exponential equation. The base is 2, its exponent will be 4, and that equals x. You can even do this one without a calculator, but if you have a calculator, go ahead and write 2 raised to the 4th power. But you can have 2 times 2 is 4, times 2 is 8, times 2 is 16. So x is going to equal 16. Woohoo! Let's try another one that's just a little bit more involved. So we've got log base 4 of 2x plus log base 4 of x plus 2 equals 2. Now before we can write an exponential equation for this, we have to take those two log terms that are on the one side of the equation and condense them into a single log term. So we are going to apply the product property because we are adding. So we're going to make it be written as log base 4, and the arguments of 2x and x plus 2 are going to be multiplied together, and that's what equals 2. So now I have a single log term that I can write an exponential equation for. 4 is my base, 2 will be my exponent, and that equals, now keep in mind, I'm going to take this argument 2x times x to get the 2x squared, and 2x times 2 to get the 4x. So I just distributed that. Now, 4 squared is going to be 16. So 16 equals 2x squared plus 4x. This is a quadratic equation. So I can set it equal to 0. So 0 equals 2 times x, or 2x squared plus 4x minus 16, and I'm going to factor this to find my solutions. The greatest common factor of all three terms is 2. I'm going to take that 2 out. So 0 equals 2 times x squared plus 2x minus 8. Now this trinomial of x squared plus 2x minus 8 can be factored into two binomials. So the 2 still stays on the outside. X squared gets factored into x times x. And the factors that multiply to 8, negative 8, but add up to positive 2 are 4 and negative 2. So those, now when I'm finding my solutions, I take those binomials that have variables in them and set them equal to 0. So x plus 4 equals 0, which gives me x is equal to negative 4. X minus 2 equals 0, which gives me x equals 2. Now, I'd love to say that this is my, both of these are my answers, but one I want to do is check these. It's extremely important that we check these because we cannot have an argument in our original equation up here that has a negative argument. So when I put negative 4 in right here at 2x, that gives me log base 4 of negative 8. Giving me a negative argument. I cannot accept this answer. When I put 2 in here, 2 times 2 is 4. That's positive, it's fine. And when I put it into the other one, 2 plus 2 is 4. That's also positive. So I can say that x equals 2 is my only solution. So once again, let's just remember that when we checked negative 4, we found that we're taking the log of a negative number, which is not possible. Therefore, we call x equals negative 4 an extraneous solution. You can reject that. So we've gotten to through all the notes for today. Here's the homework assignment that's given to you. It will also be posted on eCampus for you. But if you could pause this at some point so that the students can start working on it, that would be fantastic. And we'll start our review tomorrow, getting ready for that test.